Today is the first real lecture, and we're going to start at the bottom with the resting potential. And so what we want to do today is just get a real concrete picture of what causes the resting potential, and just to put it in context, why are we interested in potentials? Well, like the actual potential or voltage of the cell inside the cell is kind of one of the main variables that controls whether or not the cell is going to send a spike and communicate with another cell. And so that's kind of the common currency of the cell. A lot of different things affect the potential. And so before we talk about all the different kinds of things that actually cause it to go up and down, up is depolarize, down is hyperpolarize. We have to talk about the polarized part. So why is the cell polarized in the first place? And that's the resting potential. And it's related to the Nernst potential, which is a way to calculate it for a particular ion. And it's a synonym for the reversal potential, and it's kind of the same thing as the equilibrium potential. Those are all sort of different ways of saying the same thing. But what are we talking about? So what we're talking about is this was discovered over 100 years ago, just by experiments with muscles. And so if you look at a neuron, here's a nice spherical neuron. But if you look at a muscle, it's very similar to a neuron. And when you look at how your body moves, your brain and spinal cord make synapses on muscles, and they actually cause the muscles to spike, to make an action potential across the muscle. And that's basically how you move. Because when that action potential goes across the muscle, it causes the muscle to contract, like your heart, for instance. So this was figured out originally in muscles, and they, in the early days, they didn't have like microelectrode companies, and so people used very fine knitting needles. But if you put an electrical probe into a cell and then hook it up to a voltmeter, and then hook up that to ground. Ground just means the conductive fluid that's all around the cell. What you do is you find, and then just record what the voltage is, you find, it's generally pretty negative, like 75 millivolts. So that's 75 thousandths of a volt. That's about a tenth of a volt. That's actually quite a big potential for such a tiny thing. This is a tiny cell that's only like maybe 10 microns around it. 10 microns diameter. That's a hundredth of a millimeter. So it's a tiny little thing, but it has this quite large potential. And so they actually figured out way back when what's mainly causing this. And what's mainly causing this is the distribution of potassium ions. And so we're going to sort of like escalate up to a little more complicated picture over the next couple days, but let's just start with the very basic picture. So what is what causes the resting potential? And so what causes the resting potential is the fact that you've got these channels and they're permanently open. That let potassium out. So there's more potassium inside the cell, and so some of that potassium goes out. And there's more sodium outside the cell, but that sodium can't get in. So that's fundamentally what causes the membrane potential, is the fact that the potassium can get out and there's more of it in there. So let's put a few more in there. And there's sodium outside, but the sodium outside can't get in. And so you just withdraw some positives from the inside of the cell, and it makes the inside negative. So one of the things you have to, there's a lot of sign flips here going on. So you can also have negative ions. And so if some negative ions left the cell, that would make the inside positive. So there's more potassium inside the cell, and there's more sodium outside of the cell. You just have to memorize that. I'll give you a little quick way to remember it at the end. More sodium outside, more potassium inside. Now, when people first look at this, they can say, yeah, this sort of makes a certain amount of sense. So sodium can't get in, potassium gets out. But then they often confuse it with the sodium-potassium pump. So the question is, how does the cell get that way? Well, there's this other thing called the sodium-potassium pump. So it's the, Na plus K plus for potassium pump. And you can imagine, what does that do? Well, that pumps sodium and potassium in the opposite directions. And so how does that guy work? Basically, it kind of does things at the same time. At the same time as it's pumping some potassium in, it's pumping some sodium out. And that's constantly running. And that's what makes muscles, the inside of muscles, negative. That's what makes the inside of all neurons negative. It makes membrane potential in an oocyte, like in the egg. So that one's constantly running. But the problem with it is the problem with understanding this is that people sort of get this all sort of discombobulated. That thing is constantly running very slowly, making a large concentration difference, about 10 times as much potassium that is inside the cell compared to outside. It's a pretty big ratio difference. But for practical purposes of understanding the resting potential, forget about this. So how can you forget about that? Well, that's moving lots of ions into the cell. So there's a big supply of sodium and potassium in sodium outside the cell, potassium inside the cell. But the amount here's the important point. The amount of potassium that has to leave in order to cause this minus 75 millivolts resting potential is very small compared to the amount that the sodium-potassium pump pumped in and out. And so that's why you can kind of ignore this. This is just running in the background. It's just keeping this large difference. And the large difference will always be there unless somebody makes a hole in the cell, in which case the ions will sort of run the opposite way to equalize everything. But as long as there's no hole, this guy just continuously runs. You can just ignore this. This just basically establishes the concentration difference. The membrane potential changes involve movements of very small numbers of ions relative to the total potassium ions that are inside the cell or the total sodium ions that are outside of the cell. So that's an important subtle point of how do these things relate to each other. So you can just basically forget about this. This just establishes the concentration gradient, and then a tiny small fraction of these guys leave, and that's enough to cause the resting potential. Okay, so now it's still a little bit. I'll always have problems on this. Like if you've got a positive ion and there's more of it outside of the cell, what is the what would you expect the membrane potential to be? So let's just draw one more picture just to differentiate our understanding a little better. So we said we had more potassium inside than we have outside, and then we have more sodium outside than we have inside. So let's put three out here, 3 out here, and there's some sodium inside. And then we have this this channel that's always open, and the channel that's always open, lets some potassium out, but the sodium can't get in. So this couldn't possibly occur this way because you'd have a nuclear explosion if you had a whole bunch of positive, not sort of a subnuclear explosion, if you had a bunch of positive ions with no negatives to cancel them out. So there's a whole bunch of negatives in there too. So let's put some negatives in. So here's some negatives, like a chloride ion. So let's put chloride, let's put 4 chlorides out here. So now we got a balanced situation. And before we put the channel in, say we just have a sealed membrane with this distribution, then you start off at 0. So the way you should sort of conceptualize this is, imagine you're starting at neutral. So you're starting at neutral, everything's balanced. You got the same, the charge is 0 inside, 0 outside. And so starting from zero, let out a few positives, then the inside gets negative. So that's, and I obviously didn't draw enough of these. There's a gazillion of these, and very few of them have to actually leave in order to cause the resting potential. So what can we do to calculate? What's the equation to calculate what resting potential we would expect? And this is an important equation. It's very simple. I usually don't require, no, usually, I've never required somebody to actually calculate with it. I really just want you to sort of get what the meaning of the equation is. It's called the Nernst equation, and it's actually, to derive it, it's a lot more math. We have to, talk about the Boltzmann distribution. It has to do with diffusion of ions. But the equation is very simple, and so let's just look at the equation and just operate it to see how it works. So for a particular ion, for any particular ion, the equation is first a constant. So that's temperature, and we've got the natural gas, the ideal gas constant in there, a couple other constants. So those are just constants. And if we just take those guys, we can replace them with 26 millivolts. So that's the units, 26 millivolts. And so that's just 26. And then we multiply that by 1 over the charge. So the charge, so sodium is +1. So that's 1 over 1, so that's just 1. Calcium is +2, so that would be 1 over 2, 1/2. If you had chloride there, that would be 1 over -1, so that's a -1. So the sign of the, but that's already kind of common sense. If you let out some chlorides, it's going to make the inside positive. If you let out some potassium, it's going to make the inside negative. And then finally, the business end of the equation is the natural log. We'll plot that out of the following thing. And what it is the concentration of the ion that's outside of the cell. That's the way a chemist would write concentration with brackets, divided by the concentration of that same ion inside the cell. So now what we want to do is try to look at how that's a better one, how that equation works. So first we have to sort of get some feel for the natural log. And so the natural log, that function there, ln of x, what does that actually look like? So if we plot that out, we get something that looks like this. That's what the natural log, a graph of the natural log looks like. And so this is 1 right here. So say that's x going in that direction, and this is ln of x going in that direction. So that's what the natural log looks like. So, and let's identify what this guy is. So this is basically the Nernst potential, which means the it's in millivolts because I used those particular constants. So it's in millivolts of inside of cell. So remember, it's the inside of the cell, relative to outside. So if we look at this equation, if the concentration, so when you get an equation like this, you just have to fiddle with it. It's a small, simple machine. You stick stuff into it and then it gives you an output, and you just have to, you can do that just for this little piece here, just the ln of that thing. And so if you look at how the equation works, it's the concentration ratio. So it's not actually the total amount. So if you had, say, 10 millimolar outside and 100 millimolar inside, that's the same as 1 millimolar outside and 10 millimolar inside. So it's just the ratio of the concentrations, not the actual concentration itself, interestingly. But if you look at this, if it was the same, then ln of 0, so ln of 1, so ln of 1 right here gives you 0. So that's what we expected just from our very simple sort of poker chip idea of the ions. So that if you've got like some ions inside and outside, and they're all balanced, like 4 inside, 4 outside, then everything is going to be no membrane potential, no tendency for the ions to leave or come back in. So and then we can, this is the curve that describes what the potential is going to be. So if you have like 10 to 1, well then, say you had 10 times as much in here as out here, and then you'd go out to 10, figure out what this number was, multiply it by by 1 over the charge, multiply it by 26, and then you get your answer. So that's how you could actually calculate for any single ion distribution what the membrane potential would be. And so like I said, it's not as important to sort of remember it as just to look at it and just try to sort of figure out like what the meaning of it is, just tear it apart. And there's the natural log. Here's what a natural log, you just Google natural log, remember what the natural log function looks like, and just get an idea. And so you can see if your concentration ratio is more outside and you've got a positive ion, you're gonna end up with a positive Nernst potential. But if there's more inside, so this number will be below 1, then you're going to end up with a negative Nernst potential, like in the case of potassium. Okay, so what what are what causes this? So the first thing that causes it, which we mentioned already, was the differential concentration. In out. So that's the first thing. But if you just had a sealed cell without any channels in it, nothing would happen because the ions can't get in or out. And so the second thing you need is a semi-permeable membrane. And if it lets things go both directions, even if you've got a concentration difference, what's going to happen is the sodium is going to go in, and the potassium is going to go out, and it will stay 0, and nothing will happen. So semi-permeable. so what happens, what stops it? So this is an important point that's usually not mentioned. So what stops the ions from just, there's more potassium inside, why don't they just keep diffusing out? So that's essentially what this equation is describing. This equation is describing the balance. So, diffusion stops. It doesn't really stop. What happens is it gets equal going in and out. That's a fine point. But the diffusion stops, when the tendency to diffuse, which is due to 1, that concentration difference, is balanced. That's the point. Balanced by buildup of charge. So what stops it? So you've got the cell there. The channel's permanently open. The potassium is diffusing out. Why doesn't it just keep diffusing out? So what stops it is, as you withdraw the potassium, the inside gets negative. And when the inside gets negative, it's going to attract the potassiums back in. And so when this guy's getting ready to diffuse, he's going like, well, it's actually pretty attractive in here because the inside's negative, and so I think I'm just going to stay. So on average, same number that go in will go out, and so you'll reach the equilibrium. So that's the fundamental insight here, is that it's a balance between the tendency to diffuse and the buildup of charge resulting from the diffusion. So that's why it stops. And the channels stay open forever. They're not. They just stay open and cause. But it reaches this point. And so let's just talk about how to. And then forgot these are permanently open. Yeah. So let's talk about this equilibrium idea, because then there's the reversal potential and the equilibrium potential. What does that mean? So the way you should think of the Nernst potential is the target. It's the target potential that the neuron is trying to get to. It doesn't have to be there at all times. And so if you actually look at a cell, say we've got a cell here, there's 0, and say here's minus 70 millivolts. And say the cell membrane potential is sort of sitting around 90 millivolts. Now, if some channel opens up and excites the cell might become a little bit less negative, like minus 60. But if that channel closes, then the cell will go back down again. And so and what's it going back down? It's going back down to the Nernst potential. So the Nernst potential doesn't define what the membrane potential is, because there's other stuff in the cell that could excite it. It's just like the target. It's trying to get there. It's trying to get to 70. And so say a channel opened up and let some sodium in, because there's more sodium outside. Sodium's positive. That makes the cell a little bit less negative. What happens in this downslope here is that more potassium will suddenly start to move out through these permanently open channels. That's what's causing it to go down. And withdrawing these positives from the inside, making it more negative, aiming for minus 70. So it's the target. And notice it goes the other way too. So if, say, you somehow inhibit the cell and make it more negative, it doesn't like that either. And so what's going to happen is the potassium's in this case, now it says it's too negative, and so the potassium's aiming, the potassium Nernst potential is aiming for minus 70. And so if it got too negative, then what's going to happen is the potassiums will go out. More potassiums will suddenly go out until you get to the balance point. So that's the basic concrete representation of, what causes the membrane potential, the resting potential. So we're going to talk a little bit more over the next couple of days about, different things like current, but let's just start off with the very simplest electrical equation. So we have I for current and V for voltage. And then we've got either R for resistance or equivalently G, you'll see that more commonly, for conductance. And those are reciprocals of each other. So conductance, equals, 1 over R, and, resistance equals 1 over G. They're just reciprocals of each other. Resistance is like slowing stuff down. Conductance is the opposite. It's like how much stuff can get through. So how should you think of this? So the way you should think of this is, current is like the amount. It's the amount of flow. And voltage is just the pressure. And so you can distinguish those. You can have like a big pipe that allows a large flow or a wide open channel. But you could also have a small pipe that allows less flow at the same pressure. So those two things, you have to distinguish those in your mind. The pressure, you can think of it like pressure, like water pressure. And this guy is like, amount of flow. And so they're clearly related to each other. Because if you turn up the pressure, you're going to get more flow. And so that's called Ohm's law. So you can write it out all different ways, but the simplest way, voltage equals the current times the resistance, or you could say, voltage equals the current divided by the conductance. Or a more common way of writing the exact same thing would be the amount of current, this is the most concrete way, the amount of current going through a channel is equivalent to what the pressure is times the conductance. So so use this one. So that's these are all, all Ohm's law. So all this says is like the total amount of current you get is whatever the current pressure is times however open the channel is. How conductive is the channel. So it's a physical thing. Just think of it like a little water flow. So you can see that there's a problem here. So if you read any papers in the literature, the giant literature of sort of channelology of how, all these different channels work, the first thing you'll see is something about a voltage clamp. And so what is a voltage clamp? We have to sort of just get an idea of what's going on. So a voltage clamp is you have a cell and you've got something, an electrode in it. There's several ways of doing this, but I'll just write out sort of like a simplest one. So you've got something, measuring the voltage. But the problem is, and then what we're trying to figure out is we've got a channel somewhere on here, and we're trying to figure out, like what is the conductance of the channel, for instance. But the problem is when the channel opens up, it changes the voltage. And you can see that there's three numbers here. So we've got like how open is the channel, what is the current voltage, which tells us how much flow is happening through that channel. But the problem is if we're trying to sort of figure out the conductance of the channel by, say, measuring the voltage change, the problem is the channel, when it actually lets ions in, is going to change the voltage. And so we've got to hold in order to make a measurement of this conductance, we've got to hold one of these guys constant. And that's what a voltage clamp does. So a voltage clamp has some more circuitry that you can hook it up to the same electrode, but for this purpose, let's just imagine we've got another electrode in there. And what this guy does is it pumps in, So this guy is, pump, in, out, to keep same voltage. So why would you want to do that? Well, let's say you've got a channel, and the channel, say it's a channel that, say, is responsive to a particular neurotransmitter, or more likely a pharmaceutical drug. So here's some neurotransmitter or drug. So that neurotransmitter or drug causes the channel to open, and then some current is going to flow through the channel. As soon as that happens, that's going to change the voltage. But what's the voltage clamp is going to do is going to cancel that all out, just fix it all up and keep the voltage exactly the same. And then what you can do, so if you kept the voltage exactly the same, then all you have to do is measure the current. So if you just measure the current, essentially the amount that we pumped in here, just measure how much we pumped in or pumped out, that will then, because this guy's constant, that will be exactly proportional to that guy, so we can tell what the conductance is. So that's at first you might say, why do you go through all this trouble to do this? But the problem is you've got three variables here. And so if you're trying to, say, measure the conductance, we measure the conductance by doing something to cause the channel to open, then hold the voltage constant, and then measure the current. And then the current will essentially be proportional to how much the channel opened up. So that's how you actually sort of directly measure how much a channel opened up. There's something called a current clamp. You can do the opposite thing. We can try to hold the current constant and let the voltage vary around. And there's other reasons why you might want to do that. But this guy is a voltage clamp. And so that's why you always hear about voltage clamps. Okay, so these are all, spherical neurons. They don't really they look like sort of physicist neurons. They don't really look like, real neurons. How is this actually, implemented in a real neuron? So what, what actually is the membrane? Because we just talked about it, I just drew it as a line, but what's it actually made out of? How does it actually get assembled? And so we'll first zoom way in and just talk about like the actual, how does the membrane actually work? And then we'll zoom out and look at what a typical neuron looks like. So if we zoom way in, we find the membrane is just made out of these molecules that basically have an oily part and a charged part. So the membrane is very thin. It's just basically two molecules thick. So if you actually look at what the membrane looks like, so if here's our membrane like this, it's got all these molecules, and they've got like a charged part, so plus minus here, and then they've got these little oily tails like that. And they're arranged in a bilayer. So there's more charge here, and these guys are oily. So that's actually what the membrane consists of. And there's a lot of different molecules. Like here, there's some that are in the vaccine. But there's some in every single neuron. And what are those? An example of what are those molecules? Well, one of them is cholesterol. So you can sort of see, biology is everything's sort of stuck together. So, like I said, if you eat too much oil, not enough plants, maybe you'll get some heart problems, and that you might give you a statin to lower your cholesterol, but cholesterol is used for all different kinds of things. Like, for instance, every single neuron in your brain has cholesterol in the membrane. So cholesterol is one. Phosphatidylcholine is another one. That's another membrane component. But you might wonder, like, how does this work? Well, it works because this part is oily, and this guy is charged. And this is an example of what's called the hydrophobic effect. Hydrophobic, the water-fearing effect. So it turns out you don't have to actually, these things are self-assembling. So this is, it's self-assembling amazingly. So all you have to do is just put some cholesterol in water, and it will make membranes. And so why is it self-assembling? Because of this hydrophobic effect. And basically the way this works is, if a molecule is oily and it's sitting in water, which has a lot of charges in it, what's going to happen is the charges will kind of stick to the oily part and sort of freeze. They'll make little ice-like structures around the oily part, and that's energetically unfavorable. And so what will happen instead is the oily parts will stick to the oily parts, and the charged parts will stick where there's water. So those guys are charged, and then there's water out here. And so this whole thing just puts itself together. You don't have to actually do it. Just, a 2-molecule thick sheet will just form just with cholesterol and water. Now, what are the channels? So the channels are these big proteins that stick through the membrane like this. And there's the actual channel itself. There's the actual channel. So I've cut through this, it's kind of complicated little thing there. And so what is inside of there? Well, there's, a bunch of amino acids, and they typically are rolled up into these helices which extend through the membrane, and there's some helices over here also. And so those are amino acid chains that are rolling up into these little spirals. So these are alpha helix. And then this guy is the channel right here. So that one's the channel. That's actually where the ion gets through. And this guy up here is, say, maybe like this guy right here might be a receptor. That might be something that actually causes the channel to open. And, this might be something that causes the channel to open. So, say here's a little pharmaceutical drug that just fits right in there like that. And so we call that guy, this guy is a ligand, which is somebody that sticks into the receptor and causes the channel to pop open. And then when the channel pops open, depending on which is the inside and outside, say, some potassium, might be able to go through it like this. The inside of the channel is charged so that the ions are happy to go through it and avoid the oily parts. So these guys are all oily, but just the inside of the channel is all covered with charges. Yeah, so it's amazing, just the complexity of this. If you actually look at these things down at a molecular level, so if you take, there's something called a patch clamp. And so if you do, what a patch clamp is you come up to a cell like this with a pipette, and in the early days you would just hook it up to a little tube, and you just, with your mouth, you would actually just suck on the tube, and that would just tear off a little piece of membrane. And so that you would end up with a pipette like that with just a tiny piece of membrane on it, like that, stuck to it. And when you do that, you just get a few channels in there, and then you could actually just there's a channel, and there's some potassium going through the channel, for instance. If you record with the pipette, you can get a very, very precise representation of the membrane potential because you have such a high resistance connection between the pipette and the membrane. And if you look down there, it's actually digital, amazingly. So the channels, if you look at the current going through the channels, it's like no current, then current, and then no current, current, no current. Sometimes the channels might have like two states where it might go something like that. But it's basically digital. So the channels, they just sort of like boom, and they just sort of open and close. The helices kind of like twist a little bit, and they just pop into an open state versus a closed state. So this is current. It's actually digital, but there's so many of them that current through channel. There's so many of them that you end up with, these, it doesn't look like that. If you plus, say 100 of these, then you get something that looks like this. But that's actually sort of underlying it. There's actually sort of a digital reality under there, amazingly. Okay, so those are the channels. This is the lipid bilayer. So, lipid bilayer, and this guy's a channel protein. This is the channel pore right here. That's the actual sort of hole through the channel. This thing here. So that's, and if you read any textbook, you'll just be bludgeoned to death with all different kinds of channels, all different kinds of ligands that bind to them, all different kinds of receptors here too. I'll show you some pictures of these next week, what the proteins actually look like. Okay, so that's zooming way down. So now for the last bit, let's zoom out. Zoom way out to the level of, what is an actual, what does a typical neuron actually look like? Because they're obviously not circles. So let's just take as an example a pyramidal cell. So if you look in the cortex, you have a lot of pyramidal cells, and they're called pyramidal cells because they're sort of, somewhat like a pyramid, and they, go up, and they might have some apical dendrites. I'm drawing not anywhere near enough apical dendrites. They're sealed off at the end there. And there might be some basal dendrites coming off. But the important thing is that this cell is actually just one giant single closed surface. So that thing we were drawing as just a... So this whole thing is just one continuous closed surface. And there's sodium potassium pumps throughout the whole thing, so the whole thing is kept negative on the inside. But that surface continues to the axon. So here's where the axon comes off. So this guy is the cell body. For a large pyramidal neuron, it might be something like 20 microns. That's 1/50th of a millimeter. It's just not quite visible, but it's like extremely tiny speck of dust. And so if you look, the axon is also part of this continuous single surface. So the first part of the axon is called the axon hillock, but then there's a thin part, and that's where the spike starts. And that's called the axon initial segment. That's where the action potential starts. That's this guy. And then what happens is typically the axon will fatten up a little bit, and then there'll be a whole bunch of myelin on it. And we'll talk next time is, what does the myelin do? So this guy would be like 20 layers of myelin. Looks like an insulation. Turns out it's not an insulation. Well, the insulation part isn't the critical thing. This guy's the myelin. It makes the action potential go faster. We'll try to explain that later. But that thing will go off, and it'll go off sort of miles away. Now, the way I'm making this drawing, one of the problems with neurons is they're really hard to draw. So you have all different kinds of computer graphics, and you figure like, well, we could just do it with computer graphics. But it turns out the neuron is just an inconvenient structure. So a neuron could be like 5 inches long, but it's so small that you can't see it. So you could see it in one dimension. My example is always like a giraffe motor neuron. So you got a big giraffe motor neuron in the foot area of the giraffe. That giraffe motor neuron sends an axon all the way down to the spinal cord, to the bottom of near the bottom of the spinal cord of the giraffe. It could be 10 feet long, single neuron. But if you pulled it out and lay it on the table, you couldn't see it. So it's they're kind of inconveniently shaped. They're really long and stringy, but the whole thing is just one gigantic single membrane. And so then now, we go over to some other cortical area, for instance. And what happens is if we come up into the cortex, what will happen is the axon, the myelination will come off the axon. So here's all the myelination. The myelination will come to an end. And then this thing will branch into a little axonal arbor. So, and I'm only drawing a few. There could be like 10,000 synapses. And then what is a synapse? Well, a synapse is just a little swelling like that on one of these guys. So there's a synapse. There's a synaptic bouton, synaptic button. And so that synapse will then contact another cell. And what might that look like? Well, if this was a pyramidal cell, the pyramidal cell will have something called a spine. It's different than a synapse. So here's a spine. I drew it way too big, but there's a spine. And so what's going to happen is somebody else is going to come by, and that will have one of those little synaptic boutons coming off like that. And that will be the actual location of a synapse that will be able to open up channels. So that would be like, so these guys will be stuck onto some other cell right here, or some other spine that each one of those will be stuck onto one. So, but like I said, if you go inside one of these axons, you can see that the membrane potential will be negative if there's no spike coming down the pike. And so it's not a sphere. It actually looks like this. It's a lot more complicated. But all throughout this whole thing, there's going to be a negative inside membrane potential if the cell is at rest, and that's maintained by these sodium potassium pumps through the whole thing. So that's for example, I drew 2 there, but for example, 10,000. That might be how many. So that's synaptic bouton. This guy is an axon arbor because it kind of looks a little bit like a tree. And this is, dendritic arbor because that looks like a tree. Axon arbor. And there could be, for example, 10,000 synapses onto the cell. So we often draw just like one synapse so you can see some of the parts, but don't forget there's like a zillion of them. Yeah. Okay, so in the last negative 2 minutes, I always leave with one slightly shocking story to help you remember where the potassium and the sodium is. So, like I said before, if you get some problem with your heart and you have to get an operation on your heart, so one of the things you might wonder, well, heart's pumping around all the time, how could you possibly operate on it? And so the way this works is you open up your chest cavity, and there's the beating heart. It's inside something called the pericardium. You cut through that so you can actually get to the pericardium is just like a little plastic bag around the heart. So you cut that, and then you have the surgeon has the actual beating heart in their hand. But you obviously can't operate on the heart that way. And so what you do is you get a bucket of potassium chloride. So you get an ice bucket of potassium chloride and just dump that on the heart. Stops it right away. It just instantly stops it because all that potassium outside of the heart eliminates the membrane potential of the heart. And so when the spikes come down to sort of tell the heart to beat, nobody's home. So it stops the heart. And of course, then they immediately attach it up to the heart-lung machine to make sure everything's working. But that may be a good way to remember, like, where's the potassium? Yeah, the potassium is inside. And so if you put a whole bunch of potassium outside, cancels it out, changes the concentration ratio, and turns off the resting potential. Okay, David, I think we'll end the recording there, and I'll take some questions if anybody is still on.